All right, here we are. Now, unfortunately, almost forgot to send out the invitations last night. So I did send them out this morning. You might have been a little surprised, but yes, I did forget. But I remembered just in the nick of time. And I also am still working on the video from yesterday. It takes a while for it to be converted into the right form. It's still sitting here chugging away. When it's ready, I'll post that along with today's video. So if you're trying to catch up, this one it's taking its sweet time, but it'll be ready certainly early this afternoon. So anyway, in the meantime, yesterday we pretty much finished up chapter 6, our discussion about discrete random variables and discrete probability distributions, and in particular, we focused our attention on the binomial and the Poisson distributions. So we went through it fairly quickly. So I just want to take a quick peek at them one more time today before we dive into chapter 7. So let me just get the notes open. Let's see. Yes. Just a quick review of what we did. All right, so let's jump ahead and revisit the two distributions that we looked at, binomial and Poisson. Now, binomial, remember, is generated by a special process where certain conditions have to be met. We have to have a random process or random experiment where each trial is independent of the other trials. And then in addition to that, each trial can only have two possible outcomes, which we'll call success and failure. In the case of the coin flipping experiment, those two would be heads and tails, for example. And then the probability of success, which we're calling pi, is a constant from one trial to the next. If all these conditions are met, then we can use the binomial probability formula to calculate any probabilities that we need. All right, so there was our formula. Now remember, we took a bit of a detour to explain what this first term means. And we saw that this n choose x, as it's called, represents the number of combinations that we can create when we choose x objects out of n. This is the formal definition, and you notice it's defined in terms of factorials, where factorial itself is a mathematical operator that's defined in the following way. The first two are easy. 0 and 1 factorial are simply equal to 1. And then after that, it gets interesting. 2 factorial is equal to 2 times 1. 3 factorial equals 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And so you get the idea. And so there is a factorial button on your calculator. If you have the TI-84, it's under the math menu. If you have the BA2 Plus, it has its own separate button. And the iPhone calculator, which you may have, well, you do have it. I mean, as long as you have a cell phone. And probably the other cell phones like Android and the others, which I'm not familiar with at all, I would imagine they have a calculator app on them as well. The only thing you have to remember if you're going to use it is that when you turn it on, it looks like this. You need to turn it on its side to find the scientific version. All right, well, it's being stubborn with me. Here we go. So all these wonderful functions suddenly become available to you, including factorials. All right, so don't forget, it's there if you need it. Now, we also saw that factorial can be used to describe the number of ways that n objects can be arranged. All right, so we had a quick, simple first example. We have 3 books. We want to know how many ways to arrange them. We can either write them all out, or else we can use 3 factorial to calculate the number of ways we can arrange these books. Okay, so in other words, no matter how many objects you have, the number of ways of arranging them is equal to n factorial. Now, here's another simple example. Suppose you have room on your wall for 3 posters. Okay, Yankees, Dolly, and statistics. And so all 3 of these need to be put on your wall. How many different ways can we arrange them? Well, we already know now that it's 3 factorial, which is 6. Okay, so again, you can simply write them out, or you can go ahead and list them, or else you can use the formula. Okay, n factorial, very good. Let's see. Right, now here I've tried to briefly explain why this is happening, because for the first poster, you can pick any of the 3 that you have available to you. Once that's been chosen for the second poster, there's only 2 left to choose from. And then when you get to the third poster, there's only 1 left. So the total number of possibilities is 3 times 2 times 1, which is equal to 6. All right. Now, then the idea of the combinations is that we're not arranging anything now. We're choosing objects from a larger collection. Specifically here with combinations, the order of selection does not matter. Okay, so in this, the way this is written, we have n objects to choose from, and we choose X in such a way that the order does not matter. And we use this excellent example of Haagen-Dazs. We go to the Haagen-Dazs store in the local mall, and we see that today they're having a special with any 3 toppings can be chosen for $1. The question is, how many choices do we have? All right, so now, by the way, I just want to mention here that we're assuming here that you do not repeat any of your choices. In other words, you don't just say, give me 3 gummy bears. We're assuming that you're picking 3 different choices. Otherwise, the calculations would be different. So what can we choose? So it's pretty clear that the order in which we choose them doesn't make any difference. So we can write them all out, and we see there were 10 of them. And if you notice that, like I mentioned down here, GMC, MGC do not need to be listed separately because they actually represent the same combination. All right, the order doesn't matter. So therefore, these would both be the same combination. Now, how do I avoid writing these all out and calculating it directly? That's what this formula is for. And so in our example, we had 5 toppings with 3 to be chosen. So the number of ways of doing that can be obtained by plugging in these numbers. And when you go through the math, you'll see that you'll end up with 10. All right, there's 10 ways of choosing 3 objects from a collection of 5 when the order doesn't matter. We also showed a different type of example. When the order matters, then each selection is known as a permutation. All right, so we won't be using that in this class, but I just wanted you to know this. There is such a thing as a selection where the order matters. When that happens, they're called permutations. And the formula, of course, is different. Okay, let's see, what else did we do? Well, we brought all this together to define the formula for the binomial distribution. And we applied it to our die rolling experiment, and we calculated all of our probabilities. And we discovered that they turn out exactly the same as we saw in earlier chapters, because the rolling of the die, when we only focus on even and odds, does in fact follow the binomial process. So we could easily use the binomial distribution to calculate any probabilities that we need. And so we went through and we determined that, yes, they all match up with what we did in an earlier chapter. And so we also did a second example where we spun a wheel, and we had a very different probability distribution, because in this case, the red and the black were not equally likely. But we noticed that it is a valid distribution because all of these numbers add up to 1, and they're all bounded between 0 and 1. Now, finally, the big secret is that you can use your calculator, at least the TI 8384 series, to calculate the binomial probabilities directly. Okay, in other words, you don't have to use this formula if you've got the more advanced calculator. You can if you want to. It just isn't absolutely necessary because it really is doing everything for you. What you have to do is go to this button, second VARS, choose the binomial PDF function, and hit enter, and then the calculator will prompt you for P, the probability of success on a single trial, which is, by the way, what we've been calling pi. The X value, the probability that you're looking for, and then you enter, and the number of trials, which is 2, and we end up with the appropriate probability. Okay, so now, we also saw formulas for calculating moments of the binomial distribution, and we can see they're very simple compared to the formulas that we had earlier in chapter 5. The expected value is just n times pi. The variance is n times pi times 1 minus pi. And of course, that means that the standard deviation must be the square root of that. Okay, so we looked at some diagrams of what the binomial distribution actually looks like under different assumptions about pi. With a low pi, most of the values are over here on the left-hand side. It looks a lot like the skewed to the right curve we had in chapter 3. When pi is a half, we have a very symmetrical looking distribution. And then finally, when pi is equal to 7, you can see that this looks more like the negatively skewed distribution we had in chapter 3. All right, and then finally, we jumped ahead. We did the Poisson distribution, which is concerning how many events happen during a given interval of time. Okay, so it's very different than the binomial distribution because time is involved. It's not a series of trials. We're simply observing the passage of time and noting how many times an event takes place, if ever. So the formula is a little different than what we're used to seeing. We have this E here, which is a constant equal to approximately 2.71828. Lambda, this Greek letter lambda, is the average number of events per unit of time. And of course, down here we have our new friend x factorial. We know exactly what that means. And so in the problem that we did, we were told that the average number of messages that a person receives on his cell phone is 1 per hour. So therefore, that lambda parameter is equal to 1. The probability of receiving 2 messages in the next hour can be easily calculated with the Poisson distribution. All right, using that formula again, we plug in the numbers. Now remember, lambda is 1. So both of those lambdas become 1. And that makes this a lot simpler. And then x is 2. So we have 2 factorial down here. We ended up with e to the minus 1 times a half, which is approximately equal to 0.18395. All right, now again, just like with a binomial distribution, there's a function built into the calculator that we can use. And it's the same menu, but it's letter C, Poisson PDF. So here it's easy because all you have to do is tell it the value of lambda and the x value that you're looking for, and it will come up with your probability. Okay, then we saw that there are, of course, shortcut formulas for the moments of a Poisson distribution, just like binomial, except these are exceptionally simple. As you can see, the expected value is lambda, the variance is lambda, and the standard deviation therefore must be the square root of lambda. Okay, and then I showed you a few graphs showing you what the Poisson looks like. What's unusual about Poisson is that there's always these 2 bars that are of the same height. So here, for example, the probability of getting x equals 0 and x equals 1 are the same. And then it falls off very quickly, very quickly. With 2, lambda equals 2, the probability of getting x equals 1 or x equals 2 is the same. And then, of course, it falls off very quickly after that. And then for lambda equals 5, we see the 2 identical bars are in the middle here. And it sort of falls off on either side. It looks more symmetrical than the other ones we just looked at. Now, one thing I did not mention, which I wanted to, is if you look in the calculator under second VARS, let me give this a new title. You may have noticed when you look at that menu, second VARS, it has a lot of different probability distributions. And yesterday we used a couple of them. Hold on, there it is. If you look at that menu though very carefully, there's a couple that you might have noticed look similar to what we were doing. For example, when you went down to find Binom PDF, directly below it was Binom CDF. Okay, now what is that all about? Binom CDF is used for less than or equal to probabilities with the binomial distribution. Okay, so let me show you an example of this. This is something you only use once in a while. Very occasionally, you can get a lot of use out of it. So suppose that on average, 3 customers come into the bank to use the ATM. Okay, so there's one out in the lobby, and people come in the door for the sole purpose of using the ATM. Okay. What is the probability? So we'll do 2 things. A, what is the probability? Oh, you know what I forgot to mention? Each hour. I forgot to mention the time frame. What's the probability that during the next hour, there will be exactly 1 customer using the ATM? And then number B, this is the interesting one. What is the probability that during the next hour, there will be 2 or fewer customers using the ATM? Now, that's a very different one. Okay, so we'll start with A. So we know that lambda equals 3. So lambda equals 3. You just get that in there. So we're looking for x. Now x equals 1 because we're trying to figure out the probability that x equals 1. So if we go to our calculator and we use second VARS to find this probability, here's what will happen. And so we're picking oh, you know what I just realized? I accidentally started doing a Poisson problem. No, we're going to save that for last. Okay, hold on a second. I just realized I screwed it up royally here. I wanted to show you a binomial formula first. So let me save that for later, okay? Let's go back and do a binomial example. Then we'll get to the Poisson. Okay, hold on. Okay, so suppose that a coin is flipped 10 times. What is the probability of getting exactly 5 heads? That'll be part A. And then part B, suppose that a coin is flipped 10 times. What is the probability of getting fewer than 3 heads? Okay, so now we're ready. Okay, so once again, we're going to do binomial first. We're used to using binom PDF. I want to introduce you to binom CDF just in case it turns out to be useful, which it will occasionally. So here in part A, we're going to use the regular binom PDF. This is exactly the same type of problem we've done up to this point. So we'll go to second VARS, and then we'll go to binom PDF, which is A. And then when you get there, you'll see everything's exactly the same as what we were doing yesterday. So it'll ask you for the number of trials, which is 10. And P is 0.5, of course, because we're looking for the probability of a head. And the X value is 5. So you calculate those results, and it comes up to approximately let's say 2461. I'm rounding it to 4 places. So this is exactly what we did yesterday. All right, no problem. But now, what about part B? This is a very different scenario because it says fewer than 3 heads. So this is probability X strictly less than 3, which is the same as the probability, X is less than or equal to 2, which in turn equals the probability that X equals 0, plus the probability that X equals 1, plus the probability that X equals 2. Now that's a lot of calculations. What you would normally do is you would go to Binom PDF and calculate each one of these separately and add them up. In fact, let's do that just for the practice. So let's see, the probability that X equals 0. For that, I'm just going to steal this. So the only thing that's changing here is 0. And this probability is it's going to be very small, whatever it is. Yes, in fact, it's so small that the calculator is actually showing us scientific notation. If you notice, it says 9.7656, and at the end, E-4. That's scientific notation. That means 9.7656 times 10 to the minus 4. I'm actually glad this happened now because I didn't mention it yesterday. And it will eventually show up in one of your problem sets. And I don't want that to be a big shock to you. Sometimes in this calculator, that happens. The number's either too small or too big to represent directly. And so it resorts to scientific notation. All calculators do this, by the way. It's not just this one. The only thing that changes from one calculator to the next is the exact way they represent the scientific notation. All right, so what I'm going to do now is the same thing for X equals 2 and 1 and 2. Let's see. Okay, so for this one, I'm just going to make a couple of changes. And let's see what that does to our results. All right, so all we have to do is change that X to 1 in the calculator, which is easy on this one. So the number will be small, but not quite as small. Yeah, here we go, 0.00. Oh, by the way, you know what I forgot to do? Let's not write it like this. Let's write it down here as the proper value, 0.009656. Okay, that's what I forgot to do. When you raise that to the negative 10 times 10 to the negative 4th, you've got 3 leading zeros after the decimal point. So that's the actual value that we came up with. Now here, the number is quite small. Actually, let me leave that there for a second so you can copy it. Just remember, with negative exponents like that, the exponent it's 4 here, which means 3 leading zeros. It's always 1 less than the exponent. All right. All right, you should be caught up by now. Let's do 1. Now this time it's a little not quite so tiny. It doesn't need scientific notation. 009765, let's say. 66, close enough. And then let's do the same thing for X equals 2. It'll be a little bit bigger, but still not that big. So we go back and change it. And what do we get this time? 0.043945, let's say. All right, so now what do? We add them up. All right, we have the probability of getting no customers, 1 or 2. So we add them up. Okay, so, well, actually, sorry, in this case, it's the coin. We have, what's the probability of getting no heads, 1 head, or 2 heads? So we add them up, like we see here. All right, so we're just going to literally copy them. And so now if you notice, normally we round probabilities to 4 places, but when they're really, really small, that doesn't really make sense. So we'll keep more decimals than we normally would to avoid over rounding the numbers. Okay, now there's still going to be some rounding problems no matter what we do, but we can minimize that if we choose to keep enough decimals. Now, if you add these up on your calculator, let's see what we get. All right, and again, remember, this is an approximation. All right, it should be approximately 0.05466766. Okay, now that was a lot of work. And it turns out not to be absolutely necessary. Here's why. Because this is a less than or equal to problem, we can instead use binom CDF, which, by the way, if you were wondering, in the case of PDF stands for probability density function, and CDF cumulative distribution function. The key word there is cumulative. Cumulative means less than or equal to. And that's why we're resorting to this with a less than or equal to problem. And by the way, if you scroll through the list, you'll see there's several cases where there's both a PDF and a CDF. They're both available to you if you need them. But when we're dealing with discrete random variables, the majority of the time we'll be using PDF. This is an exception. So here's what we're going to do. We note that what we're actually asking for is the probability that x is less or equal to 2. So we'll go to the menu, okay, as usual. Second vars, B, binom CDF. And when you get there, it'll look exactly the same as what we're doing with PDF. It'll ask for the number of trials, which is 10 flips, probability of success 5. But then when it says X value, this is the tricky part. And before it meant the specific value of X, now it means this number, 2. So when it sees a 2 here, it understands this to mean the probability that X is less than or equal to 2. Whereas with the binom PDF, like here, for example, this is interpreted to mean the probability that X is exactly equal to 5. Okay, so this is a cumulative probability, although it doesn't really say that, does it? No. So let's see what it comes up with. And let's see how close we got. Pretty good. 0.05469, let's say. I've rounded a little, whereas before we got 0.054677. We're only off by the tiniest amount here. This is the actual value, by the way. What we have up here is an approximation. This number is exact. Now, in a case like this, we are able to calculate the entire result with one calculation, whereas doing it this way required 3 calculations. What if we'd asked for the probability that x is less than or equal to 7? Well, then this starts to really save us a lot of time. I mean, we would have had to do 8 calculations, everything from 0 up to 7 rather. So this less than or equal to function under certain conditions can be extremely time saving. But make sure you only use it when it's appropriate, okay? Because you might, if you use it by accident, you'll get the wrong answer and you'll never know the difference. Oh, what, really? What happened? Let's try that again. If it didn't work, let's find out why. Oh, that's a good, oh, Jesus, yes. That's a typo. Thank you. That was the problem. So try that again. Yes. This is what happens when you make up an example on the spot. 0.5. Yes, of course. Try that again and see what happens. Yeah, the calculator is pretty smart. It would have said, you know, you can't have a probability of 5, and it would have stopped right then and there. All right, did it work? I hope, I'm sure it did, yeah. Good, perfect. Yeah, that was my fault. Sorry, I just made a dumb typo. Okay. Now, like I said, now remember, just be aware, you should only save this for special occasions. All right, and that means less than or equal to. For anything else, continue to use the PDF. But it's good to know that it's here when you need it. You know, it's kind of like, what would it be like? Imagine that you're crazy rich and you have one car that you drive to work every day, and then you have another car that you just use on the weekends to show it off. That's kind of what this is like. This is the one that you use for special occasions. Now we can go ahead and look at Poisson. Now, Poisson also has 2 different functions. And, well, it'll be just like this. All right, I might as well copy this slide down here. And of course, I'll be posting this extended version of these notes, so you have a copy of this. Oh God, where am I? Here it is. All right, so this time, if you look, the letters that you're looking for are C and D. So letter C is Poisson PDF, what we've been using. And then letter D is Poisson CDF. And of course, Poisson, as you can imagine, is used for less than or equal to probabilities with the Poisson distribution. Again, you'll save it only for special occasions. All right, now we can have the example of the customers coming into the bank. Fine. All right, so we noticed the bank manager noticed that on average, 3 customers come into the bank every hour to use the ATM. What's the probability that during the next hour, there will be exactly 1 customer using the ATM? And part B, 2 or less. Actually, let me change that because I want to have a different number. Let's try 4. All right, why not? Except that this time we won't calculate the individual values. We'll just do it directly. All right, so in part A, the probability that there'll be 1 customer, so lambda is 3, x is 1. And so you do what we normally do. Second vars, C, Poisson PDF. Okay. And when we get there, we'll do exactly what we did yesterday. And that means x, a lambda rather. Okay, it always asks for lambda first. which is 3, because the bank manager noticed that on average there's 3 customers coming in every hour. And then the X value is just the 1. What's the likelihood that over the next hour, exactly 1 customer comes in and uses the ATM? All right, so that's going to work out to be approximately 0.14. 94, let's say. Okay, now what about the next one though? Let's try part B. Now this is a less than or equal to problem. Now, if we did this directly, it could take quite a while, because look what we have to do. This is the probability that X is less than or equal to 4, which equals, yeah, look at that. That's a lot of work. And it's not even just the amount of work, it's the risk of making a mistake is growing very quickly. So what we're going to do is go directly to Poisson CDF. So go to second vars, and then this time we're looking at D, which is Poisson CDF. Okay, and then now, just like with the binomial, the layout is exactly the same. So you have to be careful, because if you find yourself in the wrong one, you would never know, because it looks the same. It's very tricky. So lambda is 3, but now X is 4. Now remember what 4 means in this case. It means 4 or less. So if you type in those numbers, you see the number's going to be pretty large. Okay, it is about, 81, 53, let's say. I'm rounding it to 4 places. And that includes 0, 1, 2, 3, and 4. That's why it's such a large number. All right. So, oops, sorry. So that's something, that's kind of like a little side note that I wanted to show you, just in case you need it. Oh, and one more thing too. This is sort of, this applies to all the distributions. And this is really more of a time-saving device. If you notice, the cumulative probabilities are meant for less than or equal to. Suppose you have the opposite. What if instead, let's try this one, just so you can see how this would work. Because this is an important result too. Returning to the coin flipping experiment. The coin is flipped 10 times. What is the probability of getting at least 7 heads? Okay, now that's also a very time-consuming probability, because look what you have to do. Which you could certainly do. These can be obtained with, of course, binom PDF. But if you notice, it's not less than or equal to, so it appears that we can't use CDF, can we? Unless we decide to get clever. Okay, sometimes cleverness can help save us a lot of time in math and in statistics. So what I'm going to do is point out that the probability of getting, let's say, let's say 7 let's do it like this. You'll see why in a second. All of that equals 1. Why? Because one of those outcomes must occur with certainty. Okay, so x equals 0 plus 1, and then I left out a few here, obviously, but up to 6, 7, 8, 9, and 10. That has to add up to 1. So what I'm going to do is rewrite this. Here, x is greater than or equal to 6. Sorry, not greater than, less than or equal to 6. Plus the probability that x is greater than or equal to 7 adds up to 1. In other words, what I've done here is I've taken all of these and written them as less than or equal to 6. And all of these are now written as x is greater than or equal to 7. Aha, now we're getting somewhere, because watch what I can do now. I can rearrange this algebraically and say, well, doesn't that mean that greater than or equal to 7 is 1 minus less than or equal to 6? Oh, because now look what I can do. I was afraid that I was going to have to calculate all of these probabilities. But look what, with my cleverness, what I can do now is this. Whoops. I can do this in 2 stages. I can do compute this one using binom CDF and then subtract the result from 1. Oh, I like that idea. That means I only have to do 2 calculations. So let's do it. Let's calculate the probability that x is less than or equal to 6 using binom CDF and simply subtract it from 1. By the way, this works for Poisson as well. This is not just for binomial. But, sometimes you will run into these cases where the probability is not less than or equal to, but greater than or equal to. There is no calculator function for this, but if we use our cleverness to rearrange it, then we can get around that little problem. So to get less than or equal to 6, we'll do second vars b binom CDF. Okay. And okay, when we get there, of course, we're already familiar with this one. We're asked for trials, which is 10 coin flips. P is a half, of course, because it's the probability of a head. And now X value will be 6 because it's binom PDF, a CDF rather. It understands that this means less than or equal to 6. So I'll have 10 trials, 0.5 probability, 6 is my X, and that comes out to be 0.82812 25. All right, I'll just leave in all the decimals. It's okay. Now, the final answer then is not that number. Now, this is the only risk that you take when you do something like this. It's easy to stop at this point and accidentally say, oh, this must be the right answer, right? No, because you had to do that one more step. So remember, we're looking for X greater than or equal to 7. So you've got 1 minus 0.828125. Now you're going to have the right answer. Point 171875. So in other words, the only risk here is that it's easy to forget that when you're done at this point, where you get to this point, you still have to subtract that from 1 to get your final answer, because what we just did was calculate this value, but that's not what we need, is it? This is our final result. Oops, it's being stubborn with me here. That's exactly right. That is the whole point of all of this. Because of the fact that all those probabilities have to add up to 1, right here, this is the key to the whole thing. This is from the axioms of probability. You put them all here. They have to add up to 1. I can break it up into whatever pieces I need. So right here, really, this is the thrust of the whole problem. All right, that's why this works. All right, right there. That's why. Now, of course, that's just taken from here. All of those, one of those has to happen with certainty. So the probability of all of them added up is equal to 1. And that's why I can write this expression down here and therefore use my binom CDF to save me a fair amount of time. I mean, well, 4 isn't a lot, but it's worth trying this. Let's face it. All right, so whenever you see at least or more than or greater than, you might be able to, or it might make sense to rearrange it and do it this way. Not always. If I had said, what's the probability of getting at least 9 heads? Well, that would mean doing 9 and 10 and adding them up. Maybe you could do that. But for anything more than that, you might want to at least think about using this approach. Okay, so that's one little trick that I wanted you to see, because I didn't mention this yesterday. And in some of the homework assignments, I'm sure you'll run into this. Okay, now I think we're finally ready for chapter 7, which is our introduction to continuous distributions. Now, continuous distributions are a lot scarier than discrete, because of the fact that there's an infinite number of possible values. Now, what that means is that in order to calculate probabilities, you can't do them directly like you do here. What you actually have to do is either use a calculator or a table. The actual calculations would require some pretty advanced calculus, so we're going to not do that here. In a different class, you might, but not here. We're going to rely on the calculators and or tables to get the calculations done. Okay, so it's a very different scenario when we're dealing with continuous distributions. Let me show you the important ways in which they're different. And when we're done, by the way, we're going to introduce what is likely to be the most important probability distribution in every discipline out there that uses statistics. And that is what known as the normal distribution. You may have even heard of it before. It's so popular and so widespread that it is used in every discipline: business, biology, psychology, you name it. Everybody uses the normal distribution. It's very convenient. Many situations in the real world do follow the normal distribution. And so, in fact, what's interesting about it is, well, maybe we'll do this later on, but the people who were working on this, at least one of them was studying heights of people, and he was trying to show how heights are normally distributed, in the sense that there tends to be a fairly even number of very tall and short people within the same population, whereas of course most people are sort of clustered in the middle. So, but the idea of the normal distribution dates back to about the 18th century. In fact, a lot of the results that we see in statistics have been around for at least a few centuries. Many of these results started up, I'd say realistically, statistics itself wasn't really, there wasn't really a discipline of statistics until at least the 1600s. Unlike math, which has been around since, like thousands of years, statistics itself really didn't get rolling until the 1700s. Not sure why, it just sort of worked out that way. But so the normal distribution was written about by researchers going back to about the 1700s. It's been refined and it's been worked on, and it's, now it has the form that we see it here. But it's based on the premise that whatever random variable we're looking at can have an infinite number of possible values. All right, now, suppose, for example, X is defined as the length of time until the next phone call arrives. Because the length of time can be or have a fractional component, the number of possibilities is infinite. And therefore, X is a continuous random variable. Okay, so that, and remember, continuous simply means an infinite number of possibilities. So the formulas for calculating probabilities are, of course, going to be more complicated. Now, the formula itself, now, by the way, I just want to mention this. You notice that I use these letters PDF, binom PDF, I mentioned a little while ago, stands for probability density function. What's going to happen when we're looking at continuous distributions is that we're no longer going to use these for our calculations. We're going to stick exclusively with the CDFs. Okay, now take a look at this histogram. Imagine the following situation. I've got some kind of a random variable where I've got 5 possible values for X. These are the probabilities. And of course, the height of each bar represents that probability. Now, X is discrete because there's only a finite number of possibilities. So what we would have to visualize is, well, first, how would you calculate the probability that X is between 2 and 3? Well, in this simple case, what we would do is calculate the probability of 2 and 3 and then just add them up. All right, so there's nothing hard about this. This is what we were just doing in the last chapter. So what's different with a continuous distribution? Well, what happens now is that the number of bars is infinite. And so we have to approach these calculations a little bit differently. All right, so let's see what that might look like. So in other words, imagine if X isn't restricted to being an integer, it can have a fractional component. Then the number of possibilities is literally infinite. And for each X, we would need a bar, which in fact would not be a bar, but it would be a line. All right, so let me show you what that might look like. So I've got all these lines that represent a different possible value of X. And you might remember from geometry class that the width of a line is 0. So we're not going to be, what we're going to be doing is looking or focusing on the heights of these bars. And then, now here's where it gets really strange. Instead of adding up, if I want to know the probability that X is between 2 and 3, I can't just add up bars because there's an infinite number of them. So what we have to do instead is calculate the area between them under this curve. Okay, in other words, instead of counting up all the bars, I can't do that anymore because there's an infinite number of them. I'm going to turn to geometry now and calculate the area under this curve between these 2 points. Now that's when we need the calculators, because doing this directly, like I said, would require calculus. So instead, we're going to use the calculators or a table to come up with this area. All right, so now here's one of the consequences of this, and you might find this to be very disturbing. It suddenly becomes impossible to calculate the probability that x equals a specific value. Instead, we're only going to calculate the probabilities of intervals. All right, so like here, for example, let me throw this into this diagram. We can calculate the area between those two, but the probability that x is exactly equal to 2 is 0. And the probability that x is exactly equal to 3 is 0. So while we can't calculate these individual probabilities anymore, what we can do is find the probability that x is between the two of them. And that comes from this area. So this is one of the oddball consequences of a continuous random variable. We're not ever going to calculate individual probabilities, but instead ranges or intervals of probabilities. And it makes sense when you stop and think about it. I mean, if we have an infinite number of possibilities, the probability of reaching precisely 2, I mean, you can see it makes sense for it to be 0 and 3 as well. Like, for example, in this next slide, let's say that this is the distribution of times until the next phone call. The probability that it is precisely 0.9 minutes from now is 0, as is the probability that it's precisely 1.1 minutes. But what we can do is find the probability that it's somewhere in between 0.9 and 1.1 minutes. And we'll do that by calculating the area. Okay, now, by the way, the curves are defined in such a way to guarantee the area under the entire curve. Based on the axioms of probabilities is 1. So if we're going to treat areas as probabilities, we've got to make sure that the entire distribution has a total area of 1. Okay, otherwise we'll violate the axioms of probability. So this number could be, for example, I'm just going to make this up, 0.32, let's say, which means 32% of the total area under this curve. All right, now, just like the other chapters, this all may seem very bizarre and abstract at first, but once we start doing this, you'll see it's really not that complicated or difficult. It just takes a little getting used to. In a lot of ways, this is like learning a foreign language. You know, at first the grammar seems very strange, but after a while you start to get with the swing of things. Okay, if you've ever studied a foreign language, you know what I mean. So yes, we just have to get used to a few key ideas here, and then we can dive into the actual calculations. All right, so just in general, yes, the probability that x is between any two constants is the area under that curve. But the probability of each individual point is just 0. All right. Now, here's another strange consequence of this. So be prepared for another bizarre consequence. Because of this, unlike the previous chapter, we no longer have to make a distinction between strictly less than and less than or equal to. Let me erase this for a second. Here's why. The probability that x is less or equal to this lowercase x is the sum of the probability that x is strictly less than x plus the probability that x is exactly equal to x. But that's equal to 0 in this context. So therefore, these probabilities are the same thing. And that's what it says right here. Now, how strange is that? Now, that was not true in chapter 6, was it? No, not at all. But now all of a sudden, we don't need to worry about the distinction between strictly less than or less than or equal to. And the same thing works in reverse. Strictly greater than means the same thing now as greater than or equal to. All right, so, wow, this is a strange chapter, isn't it? Oh, yes, it is, but don't you worry. By the time we're done, you'll say, oh, what's so hard about this? And then we also have the following results, which you'll be able to put to good use. You will need these results as we go along, most likely. All right. So, is it going to get worse? No, no. Those were all the scary parts. Now we're just going to see how this distribution works. So, first, as I mentioned before, we're going to focus our entire attention in this chapter on the normal distribution because it's so important. It's used everywhere. And a lot of the results that we see in statistics are based on the assumption of normality. It's just basically everywhere. And again, it's because of a couple of reasons, because it's convenient mathematically, but also because a lot of things in the real world do seem to follow the normal distribution, like heights, as I mentioned before. So instead of, now, anytime we have a continuous distribution, we're not going to show it with a histogram any longer. We're going to illustrate it with a curve, okay? So this is what the normal distribution's curve looks like. It's often been described as a bell-shaped curve for obvious reasons. That's pretty much what it looks like, isn't it? It's a bell. And it has a lot of area in the center, and then it falls off very quickly. These are often referred to as the tails of the distribution. As you get further and further away from the center, by the way, as we discussed yesterday, we're using the same Greek letters to describe the mean and standard deviation for a distribution that we did for populations. It shouldn't be confusing. It should be clear that they are, here we're being used for a distribution, not for a population. So a few things that we need to note. The mean is right here in the center. And you notice there's a nice symmetry between the area to the right of the center and the area to the left. They are mirror images of each other. Okay, now as I said before, the entire area under the curve has to equal 1 because the areas are being treated as probabilities. The total has to be 1. If it's not, then this is not a valid distribution. This is no different than required. Remember we said before that with the discrete probability distribution, they have to add up to 1. It's the same thing here. It's just that it's not a table, it's a curve. And then finally, if you notice what's going on down here in the right-hand corner, the curve goes all the way out to positive infinity. On the left-hand side, the curve goes all the way down to negative infinity. Okay, It goes literally on forever. And in spite of all that, it still has an area of 1, which is kind of interesting. You would think it would have an infinite area, but it doesn't. It's 1. So when we calculate probabilities, we're going to be basically calculating areas under this curve. Now, there is a formula. This curve does represent a formula, just like we had with the binomial and the Poisson, but it's kind of frightening looking. And we're not actually going to use it in this class. Instead, we're going to use the calculators, but the calculators are actually using this formula to generate our results. But I think it'll be instructive to look at this formula because it'll help us understand a couple of important details. So don't be too panic-stricken when you see it. You will not be expected to use it directly. Yeah, look at this disaster. By the way, here pi makes another appearance. This time, it really is the pi that you know and love from high school, 3.141, et cetera, et cetera. And here's our new friend E again, 2.71828. But the most important detail is that you see mu and sigma in this formula. See, so in other words, the area depends directly on the mean and the standard deviation. Interesting. Now, I did mention, I think yesterday, that the binomial distribution is actually a family or class of distributions. There's an infinite number of binomial distributions, each with a unique value of n and pi. And the same thing is true for Poisson. There's an infinite number of Poisson distributions, each with a unique value of lambda. The same thing holds for the normal distribution. There's an infinite number of them. Each one is uniquely characterized by the mean and the standard deviation. In fact, I'm going to set up a brand new chart here just to quickly summarize this. All right, just so we don't forget, the binomial distribution is uniquely characterized by n, and pi, meaning probability of success. Remember, what happened? Not the pi that you know from high school. Here we go. The Poisson distribution is uniquely characterized by lambda. Okay. So as you saw all those histograms, the shape of the distribution depends only on lambda. And then for the normal distribution, we can say that it is uniquely characterized by, and that would be mu, and wait a minute. It disobeyed me. There we go. By mu and sigma. So in other words, remember the graphs of the binomial distribution, we showed 3 of them. They all had the same n, but they had different pi's. Poisson, we had all different lambdas. So what I want you to see is how the normal curve is, how it is affected by the values of mu and sigma. All right, so I've got, well, first of all, let's go back and revisit the graph that we had, just the bell-shaped curve in general. What does it look like? One more thing, I want to remind you of this key term here. Those values are called parameters. Okay, so in other words, when you hear the word parameters, These are the values that uniquely characterize the probability distribution. So binomial has 2 parameters, Poisson has 1, and normal has 2. All right, very good. Now we're ready. Okay, so here the curve is symmetrical about the mean. But what I wanted to show you in this part is that the spread of this curve depends on the standard deviation. The mean basically is the location. Because now remember, this whole line, this is actually the real number line. And mu represents where's the center or location. Sigma is the spread. And of course, the curve is symmetrical, and it also goes all the way out to positive and negative infinity. All right, so let's see some examples of how the mean and standard deviation affect this graph. So we're going to start with a case with 2 different normal distributions that have the same standard deviation but different means. All right, so if you notice, they have the same shape. Look at that. The means are different. The one on the right has a higher mean. And so they have the same shape because they have the same standard deviation, but their locations are different. So the mean tells me where that curve is centered or located. What if I change instead the standard deviation, but I keep the mean the same? What would be different this time? All right, so this time I've got 2 normal distributions with the same mean and 2 different standard deviations. Let's see how they're different. We know their locations will have to be the same, but all right, let's find out. By the way, it's not easy to draw these curves. If you're drawing them in your notes, it's going to take a little practice. They're basically mountains, tall mountains with a large, they fall off very steeply. Okay. So anyway, this is what it looks like when they have the same mean, but 2 different standard deviations. So if you notice, the one on the top has a very small standard deviation. So most of the area in this curve is very close to the center. The second one is a lot more spread out because it has a standard deviation of 10. All right, so it's really short, but really spread out. Okay. So that's how you can tell the same mean, different standard deviations. They're still both bell-shaped curves, but one is more spread out than the other. Okay. Pretty cool, huh? All right. Now, it turns out, so just like with the binomial and the Poisson, there's an infinite number of possible normal curves or normal distributions. But one of them is especially important, more than the others. So it gets its own special name. All right, so let's see what that is. Of all the different infinite number of normal distributions, the one that stands out above the rest as being the most important is given the special name standard normal. And what makes it special, and really it's for convenience than anything else, is that the mean is 0 and the standard deviation is 1. Now I put these little red arrows here just to make sure you don't forget this. This is very important. So when you hear the word standard normal, you immediately understand that that means the normal distribution with a mean of 0 and a standard deviation of 1. And by the way, when you go to do these calculations on your calculator, it will assume that you mean standard normal unless you tell it otherwise. Don't worry, we'll see that when we do the calculations, but I just wanted to mention that. But that's an indication of just how important this really is. The calculator figures, well, you're probably using the standard normal distribution. If not, you can tell us what the real mean and standard deviation are. But we'll just assume this is what you mean, just to be on the safe side. Because much of the time that is the case. There's no defaults. It's called the default setting, by the way. You don't get that with binomial and Poisson. There's no standard Poisson. There's no standard binomial, but there is a standard normal. Now, here's another important detail. As far as terminology goes, or notation, the letter X can be used to represent any random variable, but we reserve the letter Z to represent the standard normal distribution. So that letter Z is reserved for the standard normal case. This Z is a standard normal random variable. Its value is often known or referred to, and you may have heard this terminology before, a Z-score. By the way, if you notice what I'm doing here, this is a trick I picked up in high school French. The problem with some of the letters and numbers is that they're kind of similar to each other. So imagine yourself. Here's 2 and here's Z. See how easy they are to get confused? So one convention that I've adopted, which I think is a good one, is to put this little bar through the Z's to make sure there's no doubt in your mind that this is a Z. Okay, it can be awkward. You can see they're getting awfully close to each other here. So to avoid that problem, we put a little bar there. You may have done this yourself. The little bar there just is there to make it crystal clear that this is a Z and not a 2. It's like with O and 0. If you've ever been in a computer science class, this is the letter O and this is the letter 0, which is a little taller and skinnier. It's not, you can't tell them apart. So here's what we do. Put a little slash, and that means it's clearly obvious that it's a 0. In fact, I had an amusing incident based on this with E-ZPass. I have an E-ZPass, and one day, for some reason, it stopped working, and I needed a new one. So I called up the company, and I told them my license plate number, and they said, "This is strange. We don't have any record of you having an E-ZPass." Now, I've had this thing for like 20 years. So I thought, well, that cannot be right. Well, you know what happened? The license plate that I have, I'm not going to tell you the whole thing, but it looks like this on my license plate. The second half and it turned out all these years I had this license plate, I didn't ever know this was actually a 0. So when I called up E-ZPass and I read off to them OAG, no wonder they couldn't find it. It didn't exist. So I couldn't tell. I always thought it was an O all those years. And I finally found out, no, it's a 0. So I thought that was kind of an interesting application of this. So look at your license plates very, very carefully. You never know what you might see there. Okay, but anyway, the bell-shaped curve. So I've got some Excel graphs. Now you can see Excel does a pretty nice job doing these curves. Now, let's look at the standard normal curve. We want to start thinking in terms now of probabilities. Oh, actually, it's getting late here. Why don't we have our break before we dive into the next part? We're actually going to start calculating probabilities for this normal curve. And this is a fairly complicated procedure. So let's knock it off for a bit and get some refreshments before we dive into this very complicated topic. All right. Well, anyway, so I'll see you in a few minutes, and then we'll start doing some actual probabilities. Okay. All right, I guess we're ready for this. So we're going to calculate some probabilities, or at least start by learning some of the properties of the normal distribution that will make it easier to understand how the probabilities are calculated. All right, so based on the way this curve is defined, we're going to see a few graphs here. Now, this is the standard normal distribution. Remember, the mean is 0 and the standard deviation is 1. So you see what I've done down here on the bottom. These are the actual z-scores. 0 is in the center because that's the mean. And then these other numbers, of course, are 1, 2, and 3 on the positive side, -1, -2, -3 on the negative side. And because the mean is 0 and the standard deviation is 1, a 1 actually means 1 standard deviation above the mean. 2 can be interpreted as 2 standard deviations above the mean. And then, of course, obviously that means that 3 can be interpreted as 3 standard deviations above the mean. On the negative side, a -1 indicates 1 standard deviation below the mean. -2 means 2 standard deviations below the mean. And then, of course, -3 is 3 standard deviations below the mean. So the shaded region is covers the area between -1 and +1. It also represents the probability that z is somewhere between -1 and +1. Now, this is approximately equal to 68%. We'll see where that came from later on. But roughly 2/3 of the normal distribution is found between -1 and +1, or within 1 standard deviation of the mean, about 2/3. So imagine if this was, we're looking at heights. That means that in the general population, about 2/3 of the people are within 1 standard deviation of the mean. It means they're anywhere from somewhat short to somewhat tall and everything in between. Now we can stretch this out a little bit. All right. And we'll reach all the way up to plus and minus 2 standard deviations. In other words, -2 up to +2. And we'll see, of course, that area is bigger, quite a bit bigger, as a matter of fact. The question is, how much bigger? All right, so let's go to the next slide, and you'll see that the area within 2 standard deviations of the mean, okay, that red shaded area has a probability of approximately 95.44%. So the overwhelming majority of the area under this curve is within 2 standard deviations of the mean. So what that basically means is that if your height is not within this range, you're either very tall or very short, and there's only roughly a 5% chance of that happening. All right, well, I think you can see what's coming next. Then we're going to extend the curve or the shading out to plus and minus 3. And you'll see that that represents almost the entire curve. Okay, so let's see what that looks like. Man, now it's green. That covers about 99.7% of the area under this curve. So the vast, vast majority are within 3 standard deviations of the mean. So you can imagine, again, if you're dealing with heights, a basketball player might find that they are actually more than 3 standard deviations above the mean, way out here somewhere in the upper tail, which means that they're taller than almost everybody else in the population. So these are good numbers to know. We can actually calculate any probabilities that we need, but it's important to understand how the probabilities are laid out in this curve. All right, so what we're going to do now is introduce the tables. Now, I did post tables on Moodle. These tables were actually a lot more useful in ancient times when we didn't have these wonderful calculators. back in the day, I'm not sure what century this is now. Somebody had to sit down and do all of this by hand. And this is the result of their labors, which means we can use this table, even if we don't have a calculator, to calculate probabilities under this curve. In fact, maybe, I don't know, it's not likely that any one person's name is associated with these Z tables. David Laplace recognized the need for tables of the normal distribution as early as 1783, and the first normal table was produced by Cramp. And I never heard of these guys before, 1799, but they're important. Yeah, imagine, I mean, yeah, they saved a lot of people a lot of grief. Huh. But it would have been a nightmare. So we should take our hats off to these people for creating these tables, because that meant that nobody else had to. Interesting. All right. Well, anyway, so here they are. So the question is, what do they mean? Now you can see from this graph on the top, the shaded region is what we're actually looking at, which means these are all cumulative probabilities, or less than or equal to probabilities. So if you look at this example on the top, let's see if I can make it a little bigger. Here's the Z-score, and what they're telling us is that this Z-score is 1.34, which we know actually means 1.34 standard deviations above the mean. Now this, unlike what we were doing just a few minutes ago, this goes all the way down to negative infinity. This is not in between 2 points. This is from 1.34 all the way down to negative infinity. Now, they told us already the area or probability is 0.9099. Now, how do we know this? What is the tip-off? Well, what you have to do is go into this table and look for two numbers. Now, 1.34 can be written as 1.3 plus 0.04. So if you go into the table, this number comes from this first column. We scroll down and we find 1.3 right here. What about the rest? What about this 0.04? Oh, it comes from the top. So now what we need is the intersection of these two. This row and this column intersects at 0.9099. And that's where they got that information from. That's how it was done. Any cumulative probability, which means less than or equal to, can be done in the same way. So in other words, what they've just done is showed us that the probability that Z is less than or equal to 1.34 is 0.9099. The entire table is set up to do the exact same thing for any number you may come up with, for any Z-score. So just to pick another one at random, suppose we try and don't forget zeros in the center. What if I'm looking for, I don't know, 0.72? How do I figure that out? Well, once again, the trick is that you have 0.7 plus 0.02. So the 0.7 is right here. The 0.02 is up here, and where they overlap, here we go, 0.7642 is our probability. So that's what this table is telling us. Now, you may have seen some of this before. Some high schools actually do teach some basic statistics. And if they did, most likely they introduced you to this table. Now, as it turns out, though, the one thing that's missing from this table is negative values. So there's a second table that's designed to show us probabilities for negative values. Like here, for example, they've chosen negative 1.34, which is the same thing as 1.34 standard deviations below the mean. So what do? Negative 1.34 is the same thing as negative 1.3. It's actually minus, I guess I shouldn't write it like this, 0.04, but the process is the same. We start by looking for negative 1.3 in this first column. It's way down here. And then the 0.04 is up here. And where they overlap, 0.0901. Okay, so that's what it says right there. So this table is really no different than the other table, except that it's restricted to negative values, which means all the values below the mean. So this means how many standard deviations are we below the mean. Now, the tables are very useful, but the only problem here is that they only show less than or equal to probabilities. If we have something different, like for example, greater than or equal to 2.05, we have to do something different. All right, so we'll get to that in a few minutes. But just be aware, these tables are only showing what we call cumulative probabilities, or less than or equal to probabilities. There's no separate tables for these because there's really no need, as you'll see in a bit. In fact, I'm going to give you a hint. We're going to use the same clever strategy that we did before. Well, there's no point in being mysterious about it. Oh, here we go. I have to find the eraser here. Yeah. All right, there we go. I'll spill the beans right now. Just like when we're dealing with the CDF function for Poisson and for binomial, it turns out that this is the same as 1 minus. Oh, because one of these things has to be true, doesn't it? Yes. This is everything below, and this is everything above. So we can actually do this by subtracting the probability that z is less than or equal to 2.05 from 1, because these two together clearly add up to 1. Okay, so again, we'll do many examples of this. That was just getting a little ahead, but just the idea that you sometimes may need to rearrange your equation to solve for it with a table. All right. So here in this case, I've chosen 1. So what's the probability that z is less than or equal to 1? and we split it up into 1.0 and 0.00. So what I did in the slides is I reproduced a portion of that table so you can find it very quickly and easily. So let's see what that looks like. Here we go. Here's the 1, here's the 0.00. So that probability is 0.8413, or if you want to treat it as a percentage, you can think of it as 84.13%. So now we can think of this now in terms of an application. Suppose that it turns out the scores on an exam are normally distributed, and the mean is 80, and the standard deviation is 8. If your score is 88, that means that you are 1 standard deviation above the mean. Oh, so in other words, and let me just draw this separately for you on a separate graph so you can see it a little more clearly. On the exam itself, 80 is the mean. "88 is 1 standard deviation above the mean. 72 is 1 below. This is, I'm going to call this X. And down here we have the equivalent standard normal curve. And down here, this would be 0, this would be 1, and this would be -1. So the probability that X is below 88 is the same as the probability that Z is less than or equal to 1. And we just saw in the table that this is equal to 0.8413. So what that means then is that if you got an 88 on this test, you did better than 84.13% of the class, or below 15.87% of the class. So the table is showing you these standard normal probabilities. If you're dealing with a situation where you have a normal variable, but it's not standard normal, you can easily convert this X into Z by figuring out how many standard deviations you are above or below the mean. Once you have that information, you can then use the table. All right. So 88 and 1 mean the same thing. In a way, it's just like converting between Fahrenheit and Celsius. Okay, imagine the graph on the top is Fahrenheit and the one on the bottom is Celsius. There's a specific numerical relationship that exists between them. And the same thing is true here. It's easy to go back and forth between them. And in fact, there's a formula that I'll show you right now. No matter what X is, I can turn it into Z, or standard normal, by taking X, subtracting the mean, and dividing by the standard deviation. So in the case of 88, we had 88 minus the mean of 80 over the standard deviation of 8, which is +1. So that's how we know that 88 up here on the top is equivalent to 1 on the bottom. And then we can take it from there on the table. So what that means then is that even though the table is actually only meant for the standard normal distribution, it doesn't matter. We can apply it to any normal random variable as long as we use this conversion formula. Now, again, like I said before, I mean, this sounds all very bizarre and abstract, but once you've done several of them, you'll say, oh, this is not hard at all. And it really isn't. It just takes a little getting used to. Oh, and here, yeah, I did this in Excel to make it a little prettier. There you go. So there's your curve. 84.13% is below that point where we have the mean here, and the mean plus 1 standard deviation is here. All right, one more piece of practice here. What is the probability that z is less than or equal to negative 1.13? All right, so I've reproduced a portion of the negative table here for you. So negative 113, everything below that, let's find out. Now remember, this negative 1.13 can be rewritten as negative 1.1 minus negative 0.03. And so we'll go to our table and look it up. Negative 1.1 combined with 0.03 gives me 1292. It's a very small probability. So if you're scoring the test, well, let's just say you don't want to be 1.13 standard deviations below the mean, because that means only 12.92% of the class did worse than you did. All right, so why don't we look at the basic properties of the standard normal distribution? And some of these we've already actually gone through, so it's not completely new. Number one, the curve goes all the way out to positive and negative infinity. And because the curve is being used to calculate probabilities, as we've already seen, based on the axioms of probability, that implies that this entire area is equal to 1. Okay, in other words, the probability that z is between negative and positive infinity is 1, because this covers all the possibilities. And so this is going to be true for any continuous distribution. It's not just a normal curve. Now, how about the mean? The mean is in the center, and the curve is symmetrical. So what that means then is that the probability of being below the mean and of being above the mean is equal to a half. All right, so in other words, half the area is above the mean, half the area is below the mean. So these two probabilities are both equal to a half. That's because the curve is symmetrical. If that wasn't the case, then this wouldn't hold. But because of the symmetry, that means either side has to have the same area or probability, and the total has to be equal to 1. And the only way that can happen is if they're both equal to a half. All right. Now, the next one is going to come in very handy when we're using this table. For any value z, and let's just make up a number just to make it clearer. Suppose the number that I chose is, I don't know, 1.08. So the probability of being below 1.08 and above have to add up to 1. All right, I think we already mentioned this anyway. So clearly the two of these add up to 1. And so the reason why this is really going to be helpful with the tables is because if you had to figure out the probability that z is greater than or equal to 1.08, which is not on the table, you could simply turn it around, which is exactly what we did with the binomial distribution. And just write it like this. And of course, this 1.08 is on the table. So you can go look it up. In fact, let's go look it up. 1.08. Let's get some practice. On the positive table, that would be, here's the 1.0, and here's 0.08. 0.8599. So we've got 1 minus 0.8599. That's what it was, wasn't it? No, I forgot already. Yes. Okay. And that, of course, would equal 0.1401. So the black area is 8599, and the pink area, or raspberry, whatever, is 0.1401. And they do indeed add up to 1. All right. So that's pretty cool. All right, let's do another. There's a couple more examples here. Let's check these out just to get some practice. In fact, I'll tell you what I'm going to do. I'm going to get the table back. I'll erase all the stuff we don't need anymore. And rather than showing you the answers, why don't I have you do the following? We'll start with the probability that z is greater than or equal to 1.00. All right. So why don't you take a minute and come up with an answer, because obviously the more practice, the better. I don't have any prizes for whoever gets it first, but you'll have the honor of knowing that you were first. Okay, so what we're looking for is 1 minus the probability that z is less than or equal to 1. We did it this way because that's on the table. So we combine the 1.0, and here this is the 0.00 over here. And oh, we've seen this one before, haven't we? So in other words, this unshaded area is the 8413. The shaded region is what we were looking for, is 0.1587. We couldn't look it up directly because it's a greater than or equal to probability, but it's easy to convert it into a less than or equal to probability by subtracting it from 1. Okay. All right. Now let's do a negative. All right. First, let me leave that there for a minute for you to catch up. The negatives are very similar to the positives. You just have to be a little more careful with them because nobody likes negative numbers. They're very confusing. In fact, negatives, I showed a documentary to one of my classes about the history of math, and I don't remember exactly what century it was, but negative numbers were added to the real number line fairly recently compared to the rest of the numbers that we have. It took a while. I'm going to say the 11th century, maybe 12th century, whereas the actual digits that we're using were invented in the BC era for sure. So negatives were a relative latecomer to the real number system. In fact, it took a long time for anyone to think of the idea of 0. All right, so let's try negative 1.59. So I'll erase all the stuff we don't need. Okay, what's going on here? All right, so once again, it'll be a greater than. Now, this is going to be a very large number. In fact, we know that it's going to be more than a half because this whole area by itself is a half. Okay. All right, so we scroll down, but keep in mind too, the area we actually need is this piece. The area above negative 1.59 is quite large, as I said. Here's the negative 1.5. And here's the 0.09. 0.0. Oh, sorry, my mistake. No, this is the area we're looking up in the table. This is, hold on, I drew this wrong. I just noticed it. I pointed the arrow the wrong way. The number that we actually want is everything above negative 159. That's this piece. Okay, but this is what's on the table. And that number, as we just started to see, is 0.0559. So the rest of it must be, so we write it like this. Okay, 1 minus 0.0559 is 0.9441. Let me just double check. Yes, 9441. All right. Let's see. Are there any others here? Oh, now this is a really interesting case. So far, yes, this was all part 3. Now, part 4 is something we haven't seen before. This is the probability that we're in between two values. Like, for example, suppose that we're looking for the probability that Z is between 1 and 2. What do we do about it? Well, here's our basic strategy. We'll take the probability that z is less than or equal to 1, which is all of this. And then what we'll do is subtract it from the bigger probability, which is that it's greater than or equal, less than or equal to 2. And the difference between these two will give us the probability that we need. So this in between is the same as being the difference between the two cumulative probabilities. Now, this one we've seen a million times already, so let's just write it in here. 2, though, let's go look for that one in the table. Where's positive 2? Way down here. Here's 2.0, and we combine that with the column header 0.00, and we have 0.9772. So we have 0.9772 minus 0.8413, 1359. Okay. So that's our probability. So whether if we need less than or equal to probabilities, they're right in the table. Greater than, we subtract them from 1, and then in between, we subtract the 2 from each other. So that covers all the possibilities. So no matter what probability you encounter, you can easily figure it out from the table as long as you remember these rules. Now, let's take another example here. Let's go here to the positive table. And what we are going to do now is the probability that z is between positive 0.72 and positive 1.83. Now, by the way, this works whether these numbers are positive or negative. Okay, so why don't you take a minute? Let me see if I can. Oh, yeah. Try to see if I can make it all fit. All right, I think you can just about see whatever you need to do it now. Just about, yeah, that should be fine. All right. That's the starting point. Now, after that, it's easy. For 1.83, we combine 1.8 with 0.03 to come up with 0.9664. For the 0.72, I think we actually did this earlier, 0.7 and 0.2. Oh, maybe not. 0.7642. And so we just need the difference. .2022. And that's it. We're done. Okay. All right. So I did that here in the slides as well, so you can see it. So that's what we end up with. Beautiful. All right. Now there's another example here with the negatives. So let's get rid of all this old stuff. Okay, great. So we're going to calculate the probability that we're in between negative 2.05 and negative 0.67. All right, so I think there's enough. Ooh, it's a little tight. Oh, now it's small. All right, I'll tell you what. It's negative 2.05 is here. And no, that comes second. 0202. The negative 2.05. Sorry, negative 0.67. 0.2514. 0.0492. All right. All right. Oh, wait, did I do something wrong? I think I did something wrong here. No, I made a typo. Sorry, that's not right. 0.2514 minus 0.0202. That's what happened. It's actually 2312. Sorry about that. All right, so now we're getting a feel for these probabilities. Now, this one I showed you a little earlier. If you run into a problem where you're dealing with a normal random variable, but not standard normal, it's easy to convert it into a z-score so that you can now go ahead and use the table. So we've already seen this. So just remember, what are we doing here? We're subtracting the mean of x and dividing by the standard deviation of x. And what we end up with is what we call a z-score. Which we already saw with the grade example. Okay, remember, getting a score of 88 on that test was equivalent to getting one standard deviation above the mean. And so we use that to calculate the probability of getting an 88 in the class. All right, so now we're going to do a bunch of examples, but I think that we've had enough for one day. In fact, tomorrow I'm going to have to step back, I think, and review some of this because it was very complicated. But like I said, once we get rolling on the actual examples, after you do several of these, you'll say, oh, I see, it's not that hard. And it really isn't. But there's a lot of background material that we need to fully understand what we're actually doing. And this is, like I said, doubly important because this concept of the normal distribution will show up again in all of the later chapters. And in fact, if you take another stats course somewhere, you'll just be constantly seeing the normal distribution everywhere. It's just that important. So we want to make sure that we get this straight. So we'll stop right here. And now tomorrow is, of course, Wednesday, the last day of the week. I'll assign some, let's see, it would be 6 and 7 this week that will be due the following Monday. I'm not sure if I posted both of them yet, but if not, I'll do it tomorrow. And so just like last week, you'll have 2 problem sets due next Monday. Then we can start thinking about a test. All right. Before we do that, though, we'll definitely have a review session to make sure everybody's on the same page. But you'll do the exam at home like you've been doing the homework assignments. So it shouldn't be too painful. But we do want to get ready for it. Okay, we don't want to just blow through all the notes and forget about the exams. So I think that most likely, since we're only going to have 2 exams, I think probably everything up to this point right here is probably going to be the first exam. And then the rest of the content, which is chapters 8, 9, and 10, would most likely be this final exam. Okay, I think that makes sense, especially for such a short class. All right, so in the meantime, I guess we'll stop right here and we'll have lunch, I guess, and I'll see you all tomorrow. Okay. All right, you're welcome. All right, bye.